Okay. So yesterday where we left off was basically starting to understand why it is that gases exhibit these properties like pressure, volume, temperature, and how those properties can be translated into an understanding of the molecules of the gas. And so the kind of hopefully fun, but maybe annoying thing here is that we're going to use a lot of our apparatus from 3A. So looking at forces and energy and momentum in the context of molecules, and we'll see that you can get back these ideas that we've been talking about in 3B, things like pressure and volume and temperature. So any property of a container or a clump of gas has to originate somehow with the molecules of the gas. The fact that they bump into each other, the fact that they're traveling at some speeds. And so making that connection is our job today. And so this first picture shows what happens when a gas molecule hits some wall of a container. And this is the origin of pressure, right? Is that there are a bunch of molecules of gas in a container, and they're all slamming into the walls, and they're providing some force that is being exerted on each area of the container, which is a pressure. And so what you can do, and it's done in the book for you, but we're going to skip through it a little bit, is you can say before the collision, this particle has some momentum mv. After the collision, it has some momentum negative mv. And so we can write the change in momentum is negative 2 mv. And then we can use our impulse theorems from 3A that I know maybe weren't covered very thoroughly if you took 3A in summer session 1. But the impulse is related to the average force times some time interval. And putting this together, and then imagining that we have a whole box of gas instead of just one particle, we end up getting this expression for the force. So I don't want to walk through all the steps because they're a bit tedious, but they're all shown in the book in this section 13.3. And I'm happy to talk to you about them if you're interested. And so what we can do here is we can divide by area on both sides. And then this N over V, we often call this sort of the number concentration. So don't confuse this with the heat capacity or the specific heat capacity. So this is how many molecules are there per cubic meter, right? So that'll be some really, really large number. For a typical gas, there are, a normal human-sized box, there may be a mole of gas molecules. So that N over V is going to be something like, 10 to the 23. And then times the mass of the gas, which is going to be really small. So this is the mass of the individual particles. And then times the x component of their velocity, right? Because we're just in this picture thinking about the pressure on the x surface of the box squared. And we want the average of this. Okay. So this Vx squared average, this is something we're going to see a few times, or things similar to it. And what's happening there is that when you go through this derivation, or if you imagine gas in a box where it could move in any direction, you'll have just as much gas moving in the positive direction as in the negative direction. So if you just take the average velocity, like naively, you'll get 0 because there's so much going to the right, so much going to the left. So it'll just kind of cancel out. So you can turn all of those velocities, just think about their magnitude. So you could take the average speed, and that will have some value. But in physics, it's often easier to take the average of this velocity squared. because that will always be positive as well. So you'll get something that's not zero. And if you've taken a statistics course, this is related to this idea of a standard deviation, right? That's an average of a squared quantity. Or that's the difference between the average of the squared quantity and the average of the quantity. So, but anyways, so this is the pressure on this rightmost surface. But like I was just saying, for a box of gas, we don't expect it, once it's had a while to come to equilibrium, we expect it to behave the same in every direction. It can't tell the directions X and Y and Z apart. There's maybe some force of gravity, but for a gas, we'll see that that's almost meaningless. They're traveling, they have so much energy traveling at such high speeds that even the difference, in height of a pretty large box won't do much to them. And so what we can do here is we can rewrite this. So we can imagine thinking about the average of the whole velocity squared. And we probably all know and love the Pythagorean theorem, which is like, a squared plus b squared is c squared. I'm not sure if you've learned this, but it works in 3 dimensions as well. So if you have a line in 3 dimensions and you have so much length along the x-axis, so much along the y, so much along the z, you can do x squared plus y squared plus z squared equals the hypotenuse squared. So that also works for any dimension. The Pythagorean theorem works. You just have to keep adding things to the left-hand side. So for velocity vectors, these are 3D vectors. So we have Vx squared average plus Vy squared average plus Vz squared average. So that'll give you, so if you can find the average velocity in each direction, it'll give you the average total velocity basically, or vice versa. We just have to make sure to add them as squares so that we follow the Pythagorean theorem. But since all of the directions are the same, they're all symmetrical, we could just say that V squared average is like 1/3 of Vx squared average. That's just, it's 3. You got to get this right. Right, so basically what I'm saying here is Vx squared average is equal to Vy squared average, which is equal to Vc squared average. So we could just say that the total velocity squared average is just equal to 3 times the velocity squared average in some direction. And so now we can actually go back to our formula up here. And so instead of Vx squared average, we can replace that with 1/3 V squared average. So the pressure in a box of gas is this number density times the mass, and that's the mass of the molecules, the gas molecules, and then times this V squared average over 3, right? We're taking this equation down here and dividing both sides by 3 to plug in. And this V squared average has a name. It's called VRMS squared. So the RMS stands for root mean square. And the idea, let me make sure I get this right. And actually, sorry, I put this on the next slide. Yeah, the idea is that if you take the square root, so this is root mean square. And you can see that that's the order of operations here. So the RMS velocity is the square root of the mean of the square of the velocity distribution. Okay, so I know it's a lot to keep track of, but I wanted to just show you a picture here. So we have the speed of the molecules on the x-axis, and the number of molecules at each speed on the y-axis. So this is called a distribution. So this is the velocity distribution. It tells you how many molecules are moving at each speed, basically. And this distribution has a name. It's the Maxwell-Boltzmann distribution. If you take a statistics course, you'll learn that it's just a chi distribution, which is a variant on a Gaussian. But what I want to point out here is that the most probable speed, which is the peak of the distribution, the average speed, which is what happens if you just take so you ignore the plus or minus signs and you just average all of the values of the velocity, and the root mean square speed, which is the average of the square root of the average of the square of the velocity, they're all very similar. So we develop all this notation to talk about them. But at the end of the day, in physics, if you're asked, like, what's the average speed of a gas molecule, you can just basically say the RMS velocity. It's oftentimes a lot easier to find, and it's within 10% usually the same as the mean speed. But going back to here, I'll just write this on this slide instead. So we have the pressure is Cn times m times V RMS squared over 3. And so this equation, if we know the RMS velocity, is useful for finding the pressure, but usually we're working the other way around. Usually we know more about the container of gas as a whole, and we want to understand what are the molecules doing. So oftentimes you'll see this written as V RMS, you'll rearrange it as 3p over Cnm square root. So this is one of two formulas we'll have for finding the RMS velocity of gas molecules based on the macroscopic values of the gas. Okay, so if you know the pressure of the gas, and then remember to get this mass, we need to think about the periodic table, right? Whatever its molecular weight is or something like that. And so to give you an example of this, we have a container of helium. So it's at a pressure of 200 kilopascals. And it's at a temperature of 60 degrees Celsius. So we can just go ahead and convert that into Kelvin. So 273 plus 60 is 333 Kelvin. And they want to know what is the RMS speed, the root mean square speed of this box of gas. So effectively what they're asking is, what is the average speed of these gas molecules? Right? There's a lot of terminology here, but it's hopefully an understandable question that you might have is, imagine this room, you ask yourself, I know the molecules of air in this room are bouncing around pretty fast, but how fast? What's the average speed? And so we have a formula for this, which is the one we were just writing down. V RMS is the root 3p, and I'll just write the concentration out, N over V times M. But we don't know most of these things, right? So how do we get N over V and P from what we do know? I guess we know P, but we don't know N over V. Where do we get that? So it's a box of gas. So anytime we have gas, what tool do we always have at our disposal that often comes in to save the day? Yeah. Ideal gas law, exactly. So we have PV equals nRT here. It's easier to use that in KBT version, which is the same thing. We've just taken Avogadro's number into the ideal gas constant and called it KB instead of R, right? This KB is just R over Avogadro's number, so that we can talk about the number of molecules instead of the number of moles, which is what physicists sometimes want to do. And so we can rearrange this equation to have N over V equals P over KBT. And now we can plug in to get a concentration. I get roughly so this is like a little under 100 moles, basically. 10 to the 23 is about Avogadro's number. 6 times 10 to the 23. This is 4 times 10 to the 25. So around a little under 100 moles of gas here in this, per cubic meter of this container. And then we also need to find the mass of helium. And so can anyone tell me, how do we find the mass of helium? So what you can do is you can just say, well, protons and neutrons basically have the same mass. So helium has, the most common isotope is helium-4. So it has 2 protons and 2 neutrons. And so if you look at what's the, atomic mass or the molecular weight, whatever you want to call it, of helium on a periodic table, it'll say 4 because most helium is helium-4. And so we just have to do 4 times the mass of a proton, which is something that you just have to look up or have given to you, at least in this class. There are ways to derive it if you're curious, but here we can plug in those numbers and get something like 6.6 times 10 to the negative 27 kilograms. So very, very small mass. And now we know everything we need to find the RMS velocity, right? We have the pressure, we have the number density, and we have the mass of the molecule. So we plug all of these things in and we get roughly 1400 meters per second. Which again, crazy fast. Okay, these are unimaginable speeds. Faster than very, very fast planes at this point. So the speed of sound in meters per second is around 300 to 400. And so if we could compare these speeds to the speed of sound, we would see that we're going like Mach 4, which would be considered fast even for things like jet airplanes. And that's just the average speed. So in fact, there's a whole distribution, and there will be some helium molecules in this container going significantly faster. It's just that, very similar to any Gaussian distribution, it tapers off exponentially. So there'll be fewer and fewer gas molecules going much faster than this, and fewer going much slower than this. Okay, any questions about how we find the RMS velocity? Yes. Yes, so you would look, so we'll probably just give some of these things to you in like a quiz or a final problem. But the way you do it is you look at a periodic table, and for each element on a good periodic table, there'll be little numbers there that are larger than the atomic number of the atom. And those are telling you basically how many nucleons it has on average. So how many protons and neutrons it has. And so for helium, almost all helium in the universe is helium-4. So it has 2 protons and 2 neutrons, right? All helium has 2 protons, but most real helium is an isotope with 2 neutrons. And so since protons and neutrons have basically the same mass, we just have to multiply the mass of a proton by 4 to get the mass of the helium. Yes.
Could you explain why you use KB?
Yes. So we don't have to, but we do have to somehow use Avogadro's number. And KB is just the ideal gas constant over Avogadro's number. So it just makes your life a little easier. It makes it one step. But what you could do is you could start with the regular ideal gas law, PV equals nRT, and you could find the number of moles per volume is, P over RT. So this is just some number. And once you find the number of moles per volume, you could multiply that by Avogadro's number, and you would get the number of molecules per volume. So if we just do, so then if we take this P over RT, we just have to multiply this by Avogadro's number, and we would get N over V. So you see capital N is a number of molecules, which is going to be something ridiculously huge. And little n is a number of moles, which is going to be like a normal value, like, a couple or something. So the PV equals N kBT. It's really just the same thing as the ideal gas law. We've just went from talking about moles to talking about molecules. So we had to put a factor of Avogadro's number into the constant. And while I'm mentioning this, I should mention that because of that, KB, Boltzmann's constant, is super, super small. We'll see that be important later. But anytime you see KB showing up, you should say, I expect the result to be significantly smaller than whatever the input was. Because, KB is something like 10 to the minus 23, an inverse Avogadro's number. Okay, any other questions about this one? Good. So I know there's a lot of stuff on the slide. So actually I did put the definition of KB and its value down here. So we just take the ideal gas constant, divide by Avogadro's number, and we get KB, which has units of joules per Kelvin. And that's important. We'll see when we get to entropy soon. Those are the units of entropy, joules per Kelvin. And so, okay, let's dive into what these equations are trying to tell us, because there's a really nice story here. So, and if you're doing the thermoregulation project, this will be very relevant to you. So we have a box of gas with a bunch of little molecules in it. And we could ask ourselves, what is the kinetic energy for each little molecule? So that's what this epsilon is. This is the kinetic energy. So this is kinetic energy for a molecule of gas, or an atom of gas if it's monatomic. And so that's just 1/2 mv squared. It's the same formula we learned in 3A. The gas molecules have a tiny, tiny mass. They have a pretty big velocity. And so they each have some amount of energy, but the mass is so small that the amount of energy they have is pretty minuscule on their own. But what we can do here, and what I want you to notice, is that if we want to find the average energy, right? These gas molecules, some are going fast, some are going slow. We can take the average energy, and this will be 1/2 mv squared average. And look at that, we have an average of a v squared. That's something to do with the RMS, right? So that's 1/2 mv RMS squared. So that's the average energy for one of these gas molecules. And then what we can do is we can put that into the pressure equation we had earlier. So we were working with this pressure equation, and you can see that this equation has an m in it and it has a v RMS squared in it. So it's already really close to the kinetic energy, the average kinetic energy. So all we have to do is put a 2/2 in this formula. So we put a 2/2, and then we group one of those with the m and the v, so that this is the average kinetic energy of the gas, like each molecule. And then this extra 2 hangs out in the numerator. And what we get is an equation relating the pressure to the number density and the average energy of the gas molecules. Okay. And then we can just rearrange things a little bit. So we have, just to write this out, P is 2/3 N over V epsilon average. And so if we remember that this is a gas, then we also have the ideal gas law. It's simultaneously true. You know, the ideal gas law, it's always hiding there in the background in all of these problems. And so what we can do is we can rearrange this so that we get E average is PV over N times 3/2. But PV over N from the ideal gas law is just KBT. And so at the end of the day, we get our final result, the one in gray, which is that the average energy of a gas molecule is only a function of its temperature. It's 3/2 kb times its temperature. So, you know, I can give you a box of helium, a box of argon, a box of dinitrogen, some sulfur hexafluoride, which is like the densest commonly produced gas. All of these, no matter what the mass of the molecules, no matter what pressure and volume I put them under, all I need to know is I just need to stick a thermometer in them, get a temperature, and then multiply that by 3/2 kb, and I will know immediately the average average kinetic energy of one of those gas molecules. So it's a really profound result that it's only the temperature that dictates the energy for the kinetic energy for these gas molecules. And you know, this is talking about the energy of one of these molecules, which is really small. But since this is an average, what we can do is we can say that the total thermal energy is just going to be the energy from one of these particles times the number of particles. Okay, so if I have a box with 10 to the 23 molecules in it, I just have to multiply 10 to the 23 by the average energy, and I'm going to get the total energy. That's the beauty of an average, is that, you know, it's by definition able to do, you know, you can just multiply it by the number to get the total. And so we have the nice formula, 3n/2 kVt. And this is a way of immediately getting the thermal energy of a box of gas. And so it's something I've been alluding to a little bit because I can't help myself. Okay, before we get into the implications of that, I just wanted a quick summary slide. So now what we know is that we can find the RMS velocity of a box of gas. All we need to know is the temperature and the mass of those particles. And that similarly, we can find the pressure and the temperature in terms of that average energy. So all of the macroscopic properties now, we've related them back to microscopic properties like velocity and energy. Hold on one second. Yeah, I just want to skip ahead to here really quickly. And so for a box of gas like this, and they specify a monatomic gas, because what we've done is we've only been thinking about translational kinetic energy, right? When we did our kinetic energy calculation, we were thinking about 1/2 mv², which is telling you how much energy do I have due to like motion in the x direction, the y direction, the z direction. But there's also rotational kinetic energy that, you know, we touched a little bit upon in 3A. Like if you spin a wheel really fast, you can have it stationary as a whole, but because the particles of the wheel are moving around, they have some rotational kinetic energy, which is, you know, due to a different type of motion. So anyways, we'll put that aside for a moment, but I just want you to see this really beautiful result. So if you were wondering, where did those heat capacities of gases come from in the last lecture, this is where you can see, you know, this is where you can derive them basically. So we have the thermal energy for a box of monatomic gas. We could also rewrite it in terms of the number of moles and the ideal gas constant. So this formula is often easier to use. But remember that the thermal energy the change in thermal energy is the heat plus the work. And if we're not changing the volume of a gas, then it can't do any work. So if we're at constant volume, the gas can't expand or contract, so it can't like pull or push things. There's no work that it can do. So here we have the thermal energy, which is just 3 halves in RT equals the heat, which is going to be our well, for a gas we do this in terms of moles, so in CV delta T. And so what you can see here is that the CV matches this 3/2R. And so that's the result we were discussing yesterday, that for a monatomic gas, the constant volume specific heat capacity, molar specific heat capacity, is 3/2 times the ideal gas constant. So this is where you can see how that happens. And then for a diatomic gas, it's a very similar process, but the kinetic energy equation has a couple of extra bits to it because the gas can rotate. And so instead of 3/2, you get 5/2 because you have 2 extra types of motion, basically, that each contribute towards the kinetic energy. Okay, so I wanted to take a break and do a problem. Before we get into it, though, we're about halfway. So let's take our 5 minutes to stretch and talk, and we can start this when we get back.
Yes.
Gotcha. So yes, yeah, there are 2 options then. So either, there's 2 people in your group now. So either you can figure out, you can email me and we can figure out like which half of the project you would do, or you can consolidate with a different smaller group, basically. So
all of the groups are actually
they're actually, so there's other groups that have similar problems to you. So I'll probably make an announcement about it today. So hold off on deciding and look out for, I don't know, I'll try to come up with some way to match the groups if you decide that. But alternatively, you can just do some part of the project. But if you go that route, please talk to me before you do, just because I want to make sure that half you're doing is really half, basically. Because yeah, that's reasonable. Like, and the page estimate, it's hard because if you're doing like a derivation or something, or if you're trying to calculate something, you might like work on a piece of paper and take a picture of it, and so that might make the page count fly by really quickly. So just watch out for that. But yeah, each person should be doing 1 to 2 of the little stuff. But yeah, so that's the way to do it. Okay, thanks for talking to me about it.
Yeah. And that's that was fun. That's what it's. Yeah, I just, yeah, I thought right now,
Okay, so hopefully that's a helpful break. But we should go ahead and hop back into the slides here. So this problem is, I think, a nice example of a combination of a couple of the things we've been doing. So they want the mean time between collisions. And so if you remember that velocity is just a distance over a time, then this is going to be some sort of distance over some sort of velocity. And since they want the average time between collisions, we want to understand how far do molecules go in a gas before they collide. But we've already talked about that a little bit. That's the mean free path. And then we want to know how fast are the molecules moving on average, but we've also talked about that. That's the RMS velocity. That's not quite the average speed, but it's going to be very close for the types of distributions that you see in real gas boxes. And so to get lambda here, we want to go back to this mean free path formula. And I forgot to mention that I messed this up yesterday because I just wanted to write the final answer. But I had a few people ask me about it, so let me clarify. So this is okay, so this is the formula for mean free path. What I was doing first, you need to solve for N over V. So if we have PV equals NKBT, then N over V is going to be P over KB T. And that will be some number. 1 second, and I can tell you what that number is. Okay, 2.5 times 10 to the 25 per cubic meter. So this is the number of molecules per cubic meter, but now I have to plug that in to this equation for the mean free path. And the R for a diatomic molecule is roughly an angstrom. You don't need to memorize that. Well, I'll always tell you what it is, or you'll have to maybe you'll have to solve for that. But it's good to have in the back of your mind that molecules are about the size of angstroms. And so now we plug all of this into this equation for lambda. So we have 1 over 4 root 2 pi times 2.5 times 10 to the 25, and then times 10 to the minus 10 all squared. And we should get something around 230 nanometers, which is 2.3 times 10 to the negative 7 meters. Okay, so that is the mean free path for this case. So a very small distance, objectively speaking, but compared to the radius of the molecules, they can go a few hundred of their radii before they bounce into something. So it's not like a box of gas is completely packed, but it is pretty, energetic, able to bounce into itself. Okay, so the reason I do this calculation is that this is for nitrogen at 1 atmosphere at 20 degrees Celsius, which is the exact same as the problem that we're doing now, so that we can just use that result. So 2.3 times 10 to the negative 7 meters is our mean free path. And then to get our RMS velocity, since we know the temperature, it's easiest to just use this formula directly. So the VRMS is root 3 kBT over the mass of the gas. And we have to convert our temperature into Kelvin. So this is going to be root 3 kB times 293 Kelvin over the mass of the nitrogen molecule. This is where we have to be careful. So when we found the mass of helium, helium is a noble gas, so it's going to be monatomic. It's already satisfied with its electron shell, so it just exists as an atom. But for nitrogen, the M here that we'll use in these formulas will be the mass of the diatomic molecule. Okay, so you have to first figure out the mass of the of a single nucleus of nitrogen, and then you have to figure out the mass of the diatomic nitrogen. So one moment here. Yeah, so carbon-14 is the most common isotope of carbon. And so the mass of diatomic carbon is going to be twice that, so 28 times the mass of a proton. Did I get that right? No, carbon-12. Carbon-12, right? Okay. Sorry. So 24. That's better. Sorry, carbon is the 6th element, and the elements with a small number of protons have even numbers, have the same number of protons and neutrons typically. Sorry, carbon-14 is the radioisotope that you use for carbon dating. So thank you. So anyways, we plug that mass in. Once we find it, it'll be very small, and we get a RMS velocity of like 510 meters per second. And so now we can take these two things and just divide them. And we get an average time between collisions of 4.5 times 10 to the negative 10 seconds. which is, roughly half a nanosecond. Once we convert, yes. That's why, okay. My gosh, okay. Nitrogen, which is the 7th element. So nitrogen 14. Okay, so I had the mass right, but not the element itself. Okay, nitrogen, 7th element. So atomic mass roughly 14, but it's diatomic, so 28. Okay, as you can tell, I'm not a chemist. Usually only work with particles. Yes. So yes, I give the value for KB here if you need it. And it'll be like on your formula sheet. But it's just the ideal gas constant over Avogadro's number. So you can also get it that way. It's joules per Kelvin. So KB is joules per Kelvin, and then we're multiplying by Kelvin, so that'll give units of joules. But then we're dividing by kilograms, so that'll give units of meters squared per second squared, and we take the square root, so we get meters per second. So this is one of the great examples where you can go through the details and you'll get the right units, but if you just do everything in SI units, it'll just all work out. But it is good to think about what's happening with units as you're going through these problems. Okay, so I know that was a bit sloppy with the whole isotope thing, but any questions about this one? Yes. So I'll give you the mass of the proton in kilograms, or it's something that if you're doing the homework that you can look up. And so you would take the mass of the proton in kilograms and multiply it by 28. So you'll get a mass for the nitrogen of some amount of kilograms. Very good. Okay, any other questions about this one? Excellent. Okay, so we already talked about how for a so to find the constant volume heat capacity of some material, that we can just take the number of degrees of freedom over 2 times the ideal gas constant. And so what we could ask ourselves is, what would happen if we apply this to a solid object? And it turns out that for metals, it works okay. For more complex things that have some weird crystal structure or that are amorphous solids, or matter is just, there's so many ways that it can exist. It tends to not work very well. So I'm just gonna, your book doesn't say this, but I'm just gonna add the note metals here, because this is about the extent of the usefulness of this formula. And so for a metal, these molecules in the metallic crystal structure have the ability to move along, the X, Y, and Z axis, but they also have some potential energy along each of those axes because of the molecular bonds. And so those contribute towards the total energy, the average energy for each molecule. And so the D that we get here, is 6, right? So 3 plus 3. So there are 3 ways that it can move and get kinetic energy, and then there are 3 ways it can move and get potential energy. 3 plus 3. And so the constant volume heat capacity for a metal is 2R. And then, as we talked about, the constant pressure heat capacity is CV plus R. And so this is 3R. And as weird as this sounds, when we're dealing with solid or liquid objects and we're trying to extend these ideas of gas heat capacities, we should actually use the constant pressure values rather than the constant volume values. Now, for a solid object, both of those things are in reality going to be constant, but the constant pressure values are conveying the fact that the object has the ability to do work. And for solid objects, that's also true. And so when we're trying to decide which heat capacity to use, I'll just note that for solids or liquids, we'll want to use the constant pressure heat capacity. And so when we then just do in CT, we get the thermal energy for a metal. And it's, again, just a function of how much metal we have, how many moles, and what the temperature of the metal is. So it's a really nice relationship. Yeah.
It's 2R and not 3R. 6
Yes, that's a very good question. Sorry, this should be 3R. And then I'm confused about what the book's doing here. Because, so this, what you're saying is true. And it's also true that constant pressure heat capacities are better to use for solids. So I think this should be larger. But anyways, we'll just ignore this for a moment then. Oh, and no, okay, I still can't use colors, huh? Okay, so you're right. The constant volume for a solid is 3R. Thank you. And in general, we should be using constant pressure. I'll go back and maybe make an announcement about this because it's a bit confusing to me in the moment. But anyways, the thermal energy of a solid formula as 3 in RT does work. And the important thing really about it isn't the 3, it's just the fact that it's temperature dependent. But thank you for pointing this out. I would much rather be accurate on these issues. So yeah, 6/2 is 3. And so just be careful with this though, because this is a molar heat capacity. So in order to find the typical specific heat capacity, we would want to convert that into joules per kilogram Kelvin instead of joules per mole Kelvin. So right, this will give you something in joules per mole Kelvin. Okay, so like I said, I'll make a note about this. And then I just like these pictures to help you imagine what's happening in these degrees of freedom. So, you can probably imagine things moving in the X, Y, and Z direction. So I didn't include those. But if we have a diatomic molecule, you can imagine that there's some rotation in the Z and the Y direction, and that and the X direction. But the X direction rotation is symmetric. So we don't count this as a degree of freedom for a diatomic molecule. And then we also have these vibrational modes of freedom. And so we get 3 from translation, 2 more from rotation, and 2 more from vibration. And so as we discussed yesterday, for a diatomic molecule, so any gas that's not a noble gas, we get a constant volume heat capacity of 5/2R. And the reason is that normal temperature ranges happen to fall in this region where rotation is an active mode of motion, but vibration isn't. So gases in normal conditions only have energy in translational motion and rotational motion, not in these vibration modes. And that's just because molecular bonds are very stiff springs. And so it takes quite a bit of energy to cause them to compress and expand. And so that can only be achieved if you're at a few thousand Kelvin. And by that point, the molecules themselves tend to start to turn into a plasma. So the viability range of the 7/2R is very limited for the constant volume heat capacities. Okay. Now we've talked about thermal equilibrium quite a bit, but we haven't really gone into detail on how to calculate the energies involved in systems placed in thermal equilibrium. So what you can imagine is if you have a hot region and a cold region, that they each have some thermal energy associated with them. So if these are gases, then that thermal energy is just, or monatomic gases, is just 3/2 N kBT. And so we can calculate the energy for each side. We could call this E1, we could call this E2. And they have corresponding temperatures, right? T1 and T2. But notice that the thermal energy doesn't just depend on temperature, it also depends on how much gas we have. And so when two systems come into thermal contact, and the hot system, the system at a higher temperature, will give energy to the colder system until a point where they've both come to the same temperature. And then you can ask yourself, how much energy do they each have now? And that's what these, it's basically just a weighted average equations are for. So you find the total thermal energy, the sum of the two subsystems thermal energies, and then you give a proportional amount of energy to each one. That'll be the final state. So how much energy does this hot side eventually end up with? Well, it's just based on what percentage of the total molecules does it have, right? So N1 over N1 plus N2, it's just like a percent of the total molecules in system 1. And similarly for system 2. So these types of problems are actually tend to be really easy, but you just have to understand what the equation is for the thermal energy in that type of system. So for a monatomic gas, it's 3/2 N kBT. For a diatomic gas, it's 5/2 N kBT. You know, for a solid, it's going to be 3 N kBT. So there are all of these different relationships. And you can have systems where you have a gas and a solid coming into equilibrium. So you might have a mixture of them. You just have to use the appropriate one and then say that the energy is split proportionally. Yes. Sorry, just to describe what's happening in these systems, if I understand you right, we start off with a hot and a cold side, so they're at different temperatures, but by the end, they'll achieve some final temperature. And so if we want to know what final temperature they achieve, we can use these relationships. So it's basically calorimetry, but we're viewing it from the lens of the microscopic physics of the system rather than the macroscopic physics of the system. So it's very similar to those MC delta T and the NC delta T equations with heat. And in fact, this is in exactly that sort of expression. It's a relationship based on the heat transfer from one to the other being, whatever heat one part gives up, the other gains. And if we want to know how much heat they each end up with, it's just based on the relative number of molecules on each side. Yeah, so if you can find the total energy of the system, it'll be due to, you can see if you add up this E1F plus E2F, then you get N1 plus N2 over N1 plus N2. So you get this E total.
Yeah, I guess that equation where N1 over N1 plus N2.
I see. To find the total, okay, so there are a couple of ways that you might be asked to approach these problems. So did I put an example of this? Okay, I don't think I did. Yeah, so usually you'll be asked something like, how much heat is transferred from the hot side to the cold side? And then what's the final temperature of the two systems? And so to do that, you can replace this E total with a, if they're both monatomic gases, 3/2 N1 plus N2 times that final temperature. And that would be the final, or the total energy in the final state. And so you can see that this E1F is just N1 times 3/2 T final. And you can use the same type of calorimetry methods that we were talking about earlier this week or last week to find this final temperature. So generally you'll want to find the final temperature first, you'll want to find the heat transfer first and then use that to find the final temperature. So, the example is if you have a hot side and a cold side, then you know that however much energy the hot side gives, the cold side receives. So you can equate those two amounts of energy. And you'll have one variable in those, which is like the final temperature. And so you can use that to find the final temperature and use those temperatures to find the energies of each of the systems. But you might also just be given problems where you're asked to sort of describe how the total energy is related to the energy of each subsystem. And I just want you to know that it's proportional based on the number of molecules. And critically, it doesn't depend on the mass or the heat capacities or anything like that. The way the energy is split is solely based on the number of molecules in the system. That's the critical fact. Okay, so unfortunately, we're going to have to leave it there for today. But before you go,